Hello everyone, welcome to our presentation on enhanced ECG classification using deep convolutional neural networks. My name is Zakaria Soon and I am excited to share our research from the Computer Science Research Laboratory at the Faculty of Science, Ibn Tufail, University Qnitra, Morocco. My co-authors and supervisors are Mr. Issa Matoshi and Mr. Munir Ejkero. In this presentation, I will cover the motivation and problem, the data characteristics, our methodology, results, and discussion, followed by limitation and future directions. So, the cardiovascular disease causes about 32% of global deaths over the world, and timely ECG interpretation is vital. Manual reading is laborious and error-prone, and automated models struggle with class imbalance and subtle morphology. We focus on an interpretable, efficient model that addresses these pain points. So, what is our contributions? Our contributions are a residual CNN with a lightweight attention model, two-stage balancing strategy combining resampling and targeted augmentation, and strong performance on MITBIH with a good efficiency accuracy trade-off. Ablations shows that augmentation and class weighting provide the biggest gains. So, the descriptive statistics of the data that we use MITBIH arrhythmia beats. It's 187 sample segments around R peaks grouped into 5 classes. The normal class, so supraventricular class, ventricular class, fusion class, and unknown class. The dataset is heavily imbalanced with 82% normal beats, totaling roughly 87,000 segments. So you can see the severe imbalance in this figure. For this reason, we applied a pre-processing and balancing pipeline. So we min-max normalize and patch length 187 to counter imbalance. We downsample the majority class and oversample the minority classes to a balanced 100,000 training sets. We also apply ECG preserving augmentation, time wrapping, amplitude scaling, and light ghost noise only to training data. So our methodology follow this pipeline. So we have pre-processing to balancing and augmentation, residual CNN blocks, self-attention to focus on silent ECG intervals, dense layer for 5-way classification. So the design keeps computation modest while improving focus on informative signals. In our model architecture, we use one-dimensional convolutional blocks with batch normalization, a ReLU, and max polling with the dropouts. A residual connection in the fourth block stabilized training. We add a self-attention model to emphasize QRST-related pattern before a final dense classifier with softmax. In training, we optimize with Adam at 10 power minus 3 batch size 128 with LR reduction of plateau and early stopping. Metrics include accuracy, precision, recall F1 score, and a confusion matrix. The augmentation applies only to the training data. Now, let's move to results and discussion. So, we achieve 98% accuracy and 97.8 F1 score overall. Normal and unknown classes are recognized as approximately 99%, while ventricular and fusion perform in the mid-19s, and supraventricular remains the most challenging. The model provides a strong balance of accuracy and efficiency. So this is our confusion matrix. Here we see most mass on the diagonal. Supraventricular class is most often confused with normal class, reflecting their closer morphologies. Ventricular and fusion have limited cross confusions, which indicates the model capture key ventricular features. So in this table we have an ablation study. So like we see, removing augmentation or class whiting caused the largest drops, highlighting the importance of addressing imbalance. Residual connection and attention each provide incremental gains and robustness. In this table, we have a comparison with the recent methods on MITBIH data. So some recent models slightly outperform us in raw accuracy, but they are typically heavier. Our, our approach is simpler and faster, making it more attractive for real-time or resource-constrained settings with only a small accuracy trade-off. So, to discuss our approach, the design emphasizes efficiency and interpretability. Attention helps indicate which ECG interval guide predictions. Our balancing strategy improves miniaturity class performance without excessive complexity. The model, of course, have some limitations. So the results are from MITBIH only with 5 bit types, which limits generalizability. Broader label also coverage and multi-database evaluation are needed. A rigorous validation splits is important to avoid overfitting and data leakage. So in our future works, we will explore transfer learning and pre-training on larger ECG corpora for rare cases, a multimodal integration for improved diagnosis, temporal modeling also, explainability enhancement beyond attention maps, real-time deployment via pruning, quantization, knowledge distillation, patient-specific personalization, and continuous learning frameworks, and cross-population validation for fairness and robustness. So, in summary, a residual CNN with attention and targeted balancing achieves competitive accuracy with strong efficiency. The approach is promising for clinical and real-time use, and our ablation validated key component. So thank you. I'm happy to take questions on the model's efficiency or interpretability and how we plan to validate across population and devices. Thank you.